Hello again, this is Al. Moving on to lesson 51 in this set. We're dealing with the topic of inheritance, and left it, reconstructed almost what we had before, with maybe one extra struct that we didn't have before. So this is the linear chain type inheritance. A goes to B, goes to C, goes to D. And in this case, this particular struct can be interpreted as either one of these structs. Since this is the lowest point in memory, any object that wishes to view this as a D would just take the first 30 bytes worth of it, and that would be a D. Anything that wishes to think of this as a C would take the first D plus this many bytes of it, and that's a C, and so on. So for any number of structs defined in this order, or in this pattern, it takes on the identity of any one of these structs, and so therefore any cast, and what I want to look at right now is casting, any cast of these objects into any of these types should pretty much return the address of the 0th C in this case, the address of the D part, the base address. So I've made a little printing out here. You don't need to worry about the details of that. This is the printout. This is unnecessary. This is something that's going to happen, so actually both these cases, well, let me just run it and I'll show you the printout. I've made some improvements to the printout, hopefully to help us understand what happens in the other type of inheritance. Okay. So here's the construction part, reverse order as expected. Then I made a little box here that draws the structure of the struct and the layout in memory, the size of each subportion. All these numbers make sense. A, as you recall, really only has 2 bytes of data, but it ends up being an 8-byte struct. Perhaps I could add a line here, giving the total, whatever that total is. What is that total? Minus $32 plus 50. Sorry, I was curious if it changed from what it was. 144. So this is a different struct from before. Assuming I haven't made a mistake. But if I recall, before we only had this part, and this part, and so this is new. And before it was 118 or 12 or something. Anyway, now I'm printing out there are various ways to cast things in in C++. Or not. This here cast where you just say put a type and a star in front and then put that in brackets and put an address. This is called the C style cast. Now I can't find any information on this in the help file because I don't know, it doesn't seem to have a category for that. However, with all the experiments so far that I've been doing, it appears as though this type of cast gives the same result as this type of cast, static cast. Reinterpret cast, okay, does nothing, essentially. All it does is returns whatever numeric value is in here. Okay? So that's what I thought this did. But that's not true, in fact. This does a little bit more than just changing the interpretation of this address. So be aware that when you do a C-style cast, you're not only changing the view of what the thing might be, but you might be changing the actual address, which is often desirable. And then the destruction in reverse order as I have here. Now, it seems like a lot of work, and in fact a lot of work went into getting this layout, but now I want to do a bunch of experiments. And I have here in these files different experiments I tried before. A few cases where this is a case where the reinterpret cast failed. And what's this one? DB center. I don't know what that means. Oh, I see it. Alright. Okay, so I'm trying various combinations of the deriving from the right or from the right and up. So here's a case where I don't know yet because I haven't run these, but I think that D and the DB section of this struct ends up being in the middle. So you've got a C, so it's essentially the same. No, not the same as the other struct. Well, actually, let's try this one. I should be able to just copy these directly now into my other working thing. Let's see what this gives. Now, whoops, not what I wanted. I'll paste it. The way I knew things were going wrong was I would take some of these results and print out a member or something. And I'm not setting any members in this particular one, but I'd like to see what the layout is, at least. Let's just see. Assuming my amazing sort function works. My super sorter 30 billion. Okay. Now, according to this, the layout of this A derives from both C and D. Okay, C and a D. And it's true, the D and the B end up in the middle. Now the order of construction. C first. Well, A depends on C, so that looks like a left to right. If that were a left to right, and I'm not looking at this. If it were left to right, C will get constructed first, and then it's done. Then we go to D, which depends on B, so it should go C, B, D, A. C, B, D, A, that's correct. And that's in fact the order of the layout. Now here's what I'm talking about. The address of the object itself is this 70, okay? And that can be read off from the construction. The C-style cast, which I previously thought did nothing, I thought it was the same as this, does not return the same answer for different casts. If I try a C-style cast of this guy to a B star, I get A8, which is the address of the B. So it actually does give me a pointer to a B, ignoring C. If I want, sorry, that was B, right? Yeah, now if I want a C, it gives me the object C, which is correct. And if I want it as a D, it gives me, again, A8, which is a D struct. B here is the base of a D. So this casting worked. Now let's look at the static cast. 78, so that's the same, okay? Static cast worked properly, but reinterpret cast, which does nothing, always just gives you the base address. It never changes this. So if we had some data in here, these casts would fail on the cases B and D. So the B and D casts would fail. Now you see a lot of these reinterpret casts and static cast, and there's another one called const cast, dynamic cast, and all these various casts. And you see them in a lot of projects, and I'm not exactly sure that people know which one they're supposed to use. And I don't know for certain which one you're supposed to use, and the help is very ambiguous on it. For instance, if I look up one of these casts, like this one, in general you use it when you want to convert numeric types such as enums to ints to floats, and you're certain of the data types involved in the conversion. Not as safe as dynamic cast, but we can't use dynamic cast on a plain old data. It does no runtime check, but dynamic cast does. A dynamic cast to an ambiguous pointer will fail, while static cast doesn't fail, which is dangerous. So they're saying, okay, sometimes it's dangerous to use this one. And then, then now there's another one called const cast. There's const cast. This is something to do with completely another thing entirely. Now I should add this to my list here. Pointer to object can be converted to a type that is identical except for the const, and these qualifiers for pointers the result will refer to the original object. For pointers to data members, so if you're casting, that would be like when we did address of A.B.D of 0 or something. The result will refer to the same member as the original uncast pointer to the data member. That sounds fine. And on the type of the reference object. A write operation through the resulting pointer might produce undefined behavior. Okay, well, again, warnings again. Cannot use constcast to override the constant status of a variable. I don't understand. Oh, if it's not constant, I guess we can't turn it into constant? I don't know. And you see these all over the place in these, especially in that source forge. Reinterpret we saw. That does nothing. Reinterpret. At least we understand that one. Static cast we just looked at. Now, dynamic cast is great, but it only works on what they call a polymorphic type. Dynamic cast type ID must be a pointer of reference to breaking changes. Okay, more warnings. See, oh dear. These casts are really a pain. It's I usually use dynamic cast, but only in a very limited, specific way. Like in the case where I might return a pointer to void in a function, in a C-style function, and then that the user might pass me a pointer back, and I want to make sure that it's of the same type that it's supposed to be, then I'll use dynamic cast in some cases like that. But you wouldn't want to rely on it too heavily. But again, it has to be a polymorphic type, which is something we haven't covered. You need runtime type information. There are some good things about this dynamic stuff, dynamic typing. Anyway, let's see if we can try another one of those experiments. Here was another one where, in both those cases, reinterpret failed. Now, what's this? What's this set? Oh, here what I've done is I've used something you don't know about, because I wanted to set some variables and then I wanted to print them out, but we don't need to. I'll take that bit away because I can tell now with the new printout what's right and what's wrong. Well, with that little box there and the way the numbers are written, you don't need this fancy food and setting variables. Okay, so now let's look at this scenario. It seems like the rule is left to right, and dependencies as you go along. So first thing is C, which depends on nothing. So my guess is we're going to see C, B, and then D, and then A for the construction order. As far as the data layout, well, A is deriving from C and D. It'll probably put C lowest in memory, as it has been before. And isn't this the same as we just saw? This is like the DV center. CD, CD, DB. Oh, it's the same. Yeah, let's try this one then. Here's a new one. Okay. Now we've got A, D, C. So, and D again from B. So the construction order is going to be B, D, C, and A. And I'm not sure about the memory layout, but I would guess, all things being equal, C always seems to end up on the bottom, and A always ends up at the top, it seems, but I'm not sure. No. Now this time C ends up beside A at the top of memory, and B and D have been squished down. And as far as the casting goes, all of the castings are correct by taking B as the base address, except for one of them, which is if you want it to be a C. In order to get a C from this layout, you have to start here. So this bit has moved up here beside A, and so that makes at least there's a C there. Otherwise, everything else is correct from starting from B, including with the C in the middle. I wonder why that is. If I wanted an A, which means the whole object, doesn't matter. B, true. C is the weirdo one, and then D. What's a D? A D derives from a B. Oh, but B is the base. I see. Okay. So again, you see the ordering's not it's not trivial. There might be some optimization in this ordering. In that, 3 out of 4 of these casts are the same. Only one of them needs to be slightly modified, and the rest can just be taken from B, provided the memory is rearranged. It's not in the order they're declared. All right. What about the construction order? B, D, C, A. Oh, it's also, of course, I guess it's always in the order of the construction. So, yeah, B, D, and that makes some sense. C and then A. We could try another example. Try and think of something. What about everything on the side? Like this. B, D, C, A. That should be the same order. That's the same order as we just had. Now let's see what this says. B, D, C, A is the same construction order. But look, it's changed. As far as the casting is concerned, only 2 of them are valid from B, A and B. Well, A always, of course. B is okay from starting from B, obviously, because that's a B. And Now the rest, C and D, are just their own addresses. A C is here, and a D is here. So they're all actually assuming, each one is assuming the address of itself. So this flat model appears to have the effect of everything pointing at itself, because nothing depends on anything else. Now how else can we mix it up? We need more. Let's make another one E. E. I can't do, well, we could try it. I think it would fail if we had two deriving from the same base class. E, let's give it an array of strings. Okay, well, that's good. That's already correct. Now, let's make B be a dependent on E. Okay, and now what do we get with this? Oh, now in this case I gotta change the number of structs to number 5. I don't think I need to change anything else. Yeah, that's true. A dot, what are we going to say? We have two things called stir. I can give it a different name, or I can be specific. I'm going to be specific and show you some language features. We have two things called stir, right? One from the C and one from the E. Okay. Now, if I want to specify which one I want, I think the correct syntax is, I think that's right. No. Ambiguous. Could be E, but I thought I was specific. So maybe it's not the same one. Maybe I got the colons backwards or something. No. I want is stir. Let me think about it for a second. Okay, it wasn't too long. You can see the clock. I had fixed this one, but I hadn't fixed this one. Now, I don't need to give these the same name, but this illustrates at least how the namespacing works within a structure. Each of those sections, how does this end up like this? In our set of structs here, each section has a kind of a name, and those are called namespaces. Come on. That works. Okay, that's correct. Missing one. Yeah, so for instance, if I want to refer to E's stir as opposed to C's stir, as I've done down here, I take the object, whatever it is, and I'm doing a dot. Dot is a dereference, and so I'm asking for the value of something. And now stir would usually be enough. It would just be offset the thing called stir. But I've got two things called stir. One of them is in E and one of them is in C. So in order to choose the E one, I use the double colons to namespace the stir to say that I want the stir that is within this namespace, E namespace. And so that should be correct. And if it's not, I'll change it. Okay, now the question is, what are we going to get with all this? We've got a funny looking mess going on here. We're in the program. Okay. No, we should have tried to figure it out first. B, so the order, without looking, going from left to right, would be E, and I could even print out constructors for these strings. E, B, D, C, A. E, B, D, C, A, correct. The layout of the data is in the same order of construction. I think we can take that as a general rule. Casting. The object is built in a weird way. E and B, you would think it's going to try and group E and B together, which it has. So it's taken this C here and moved that up to the top near A, with D on the bottom. So the C, it kind of makes sense, I guess, to put C after D, because D got constructed. If we went from left to right, D got constructed first, and we usually think of construction going down, so it kind of makes sense to put a C in between. And the point the cats. No, I'm not doing all the cats. No, it's not running. No, I should turn this into a loop, but just for quick view. I'll fix this up later. Alright. Now we got 5 casts. 3 of them are the same. A, B, and E. Well, A is always the base. E is obviously going to be, yeah, that makes sense. Yeah, A is the whole object, so that's always going to be the top. And whatever is at the top will also have the same casting value. And the next one, if it's dependent on it, will obtain that value as well. And the relationship here has E and B related. That's why the C was cut out and moved up here. And the remaining two, they're totally independent, and so therefore they each have their own pointer. Now, is there any difference between that and static cache? I see no difference. And I think that there's no difference between this and this. But I could be wrong. We have 5 objects. Let's try and mix it up a little bit more. Suppose C, something like that. So C is depending on D, which is the middle thing in the list. Let's just try it as is. What's our guess for we failed? Oh wait, no, we gotta define the class. Just simply a matter of moving it up. Now in this case, B, so E would be the first thing constructed, then B, then D, and then C. So this should be the same. If we interchange D and C, we should get the same, because the C would cause the D construction. In fact, we can take D out of here completely. We can't derive from both D and C. The question is, which one should we keep? I would say that we would have to get rid of D. Because if we just had D here, well, it's possible, I guess, that C would be omitted. Let's see what happens. Maybe we won't get a C. No, it didn't like that. Cannot convert to C star. Oh yeah, because of that's just because of my printout thing. I'm curious though about it. So let me get rid of the C part. How can I do that without making a mess? I know the C's gotta go back. Don't forget. Another C. Well, that's still too many changes. Okay. I'll get to that one later. Alright, so I think we just take the C out of here, and then, no, the D out of here into the C, and then we'll still have everything in the list. Now what do we get? EBTCA. Yeah. E, sure. B, D, and then C, and that makes sense. Just the dependencies. It's very similar to the last one, if not identical. I think we just repeated the same experiment. How about, what else can we try? B depends on E. We could remove that dependency and put the E here. And then we've got C, which depends on D. Let me try and putting that one maybe in the middle. So the center one has a dependency. Okay, so it should go E, depends on nothing, D, C, B, A. E, D, C, B, A. Correct. E and A should have the same address. Yes, they do. C and D have the same address because they're connected, and they do. And there's one just isolated on its own, B, and that's true of B. It doesn't depend on any of these. It just happens to be tagged along for the ride. So, you can go on forever trying different combinations, and it's all going to work out like what we've been seeing. Let me see how much time I've got. The complications start when you get things that can inherit from the same sort of ancestry trees or have similar roots, and in particular things that have these things called virtual functions, which I haven't gotten to, and those situations can get very complex. And like I said before, the simpler the better. There's no need for things to look like this. Let me just try and find a piece of code that does use multiple inheritance, but in a sane way. I'll just have a look, and maybe I can find something. Okay, now here's an example of something which makes some sense that it would have two separate parents. It's a type of type of dialogue called modeless. A modeless dialogue is not one of those ones that pops up and you can't do anything until you're done with it. It's like one of those ones that will keep doing something on its own, like copying some files, but meanwhile your program doesn't grind to a halt. You don't have to wait for this thing to finish to go on doing something else. So it inherits the dialogue functionality for drawing itself and whatnot, and also the functionality for something called a thread. Now, what a thread is, it's like a little process that runs inside another process. So you have a program, and it's possible to let part of your program run on its own, independent of the rest of your program, and you have to be very, very careful when you do that. But if you do that, that's called a thread. Like, for instance, something that's playing music in the background uses a thread. There's some piece of code that's running through a loop, reading data from a file and making sound come out of the speakers. That doesn't halt the program. Winamp still runs. You can do other things. It has a thread. Similarly, a modeless dialogue is something that might be for a long task, so it requires a lot of time to complete. You don't want to halt the system, so it makes sense that it should run in its own thread, but not to contain thread as a member, because this object represents the process that it's actually doing. So it is a process in itself, this object. It is a dialogue in terms of its visible appearance, okay, like a regular dialogue or a window, and it is a thread. It doesn't have a thread, it is a thread. Things don't have threads. They either are threads or they're not threads. Every running program, in fact, is a thread. If you look at the very lowest level in the runtime library, there's going to be a loop of some sort, and it's going to say, process thread messages or something, because every process is a thread, and they have sometimes multiple threads, and so on. So this is the same use of multiple inheritance, and you'll notice as well that the inheritance of this thread structure by this object is not public to the outside world. It's written this way to emphasize the fact that this is one of these things, but access to the threadness of this object is restricted to internal processing. Okay, and even the dialogue functionality uses a new keyword called protected, which means it only allows certain objects limited access to the functionality of this particular object. So there's an example of use of the kind of use of multiple derivation that you might come across that is useful. This is the correct way to do a modalist dialogue. That other stuff is just silliness, right? That's just play. Okay. Now I have a lot more to cover, and I'm going to make a list. There's still more string things and a lot of stuff piling up, and I'll have to skip some things and just point you to the files to look at. And in fact, I'm going to probably do another update on the server for the code, the source code, once I'm sure that this is okay. And whoops. Oh God. And that's it, okay? So I can't tell you about the next lesson. I won't continue much further on this particular kind of derivation, like just the topic of derivation. We'll use derivation in examples in practical scenarios rather than this theory stuff. Okay, see you next time.